very basic introduction to FEA. We're going to be just doing a two-dimensional analysis. So go ahead and double click on static structural. It will bring you to this screen, and you have these 7 modules here that they're going to start with question marks, which is good. Engineering data, you input what material you want to use and material properties. In geometry, you define the shape of what you want to do. The model is where you do all the boundary constraints, where you're holding it still, where you're pushing on it, that kind of stuff. And the rest of them, they're all on the same screen as a model, so you guys will see that when we get to it. So the first thing is double click on engineering data, and this will bring up this screen. And it's going to look really complicated. It might look a little bit different on your screens. And you might have to pull some stuff around to see things. So this section here, A. So for me, it was like really small. So go ahead and like stretch it out if you can't see that area. We're going to input a new material, and we're going to type in aluminum. And once you do that, this is what it's going to look like. It's going to show up the name, and it's going to have a question mark here. And is everyone at that point? Is anyone having struggle getting to the engineering data, typing in the material name? I could swing over if anyone's got an issue on that. Everyone good? Cool. So once you type that in, you see on the side here, you have a lot of options for data input. You have linear elastic, you have plasticity, you have creep, you have all this kind of stuff that is really complicated. The one we're going to stick with is isotropic elasticity. And we only need 2 values to input here to do all of our analysis. And the first one is Young's modulus, which I wrote on the board, 71.7 GPA. So you could type in 71.7 E9, E9 meaning 10 to the 9th, which is to get GPA from regular Pascals. And for Poisson's ratio, we're going to put 0.33. That's a pretty standard Poisson's ratio for aluminum. And when you first click on linear on isotropic elasticity, you'll see that you get the yellow boxes. So now that I've inputted all the data that I need, the yellow is gone, and it's kind of telling me like I'm good to go now. So after we have this, we click back on project. So project in the top left corner, we click on that, and it brings you back to the original screen. And now we're going to see that there's a green check mark by engineering data. So that means we're good to go in terms of inputting any kind of data for the analysis. Is everyone at that point? Does anyone need any help? Okay, cool. I'll go on. So next thing we're going to do is define our geometry. Before you double click on geometry, really important that you go on the side here, on the right hand side, under advanced geometry options, the analysis type, change that from 3D to 2D. And you have to do that while there's still a question mark by geometry. If you go ahead and define your geometry and then try to make that change, it's still going to think you want to do a 3D analysis, and you're just going to have to restart. So it would just be simpler for you not to make that mistake. So after you go and put this to 2D, go ahead and double click on geometry, or select it and press enter, same thing. And I have an older version of Ansys, and last time we did this, it just brings up this very basic CAD program where you define your geometry. And I think you guys are saying that last time we did this, it brought up some kind of like different CAD modeling stuff. CAD is CAD. It just looked a bit different. And this basic CAD program lets you, just like if you've used SolidWorks, you can make a sketch, you can make a face or an extrusion. But all we're going to do here is draw just a square, or not a square, a rectangle with the dimensions of height of 1/4 of a meter and length of 2 meters. The easiest way to do that here is we want to draw it on the XY plane. So here on the side, I have XY plane. I could go ahead and right click and click look at, and that just brings me to look right at the XY plane. On the bottom here, by modeling, I have this tab called sketching. So I can click on that. And you could do this a lot of different ways. You could draw a couple of lines. You could draw a rectangle or rectangle by 3 points. And they give you a lot of like your standard sketching tools for a CAD package. So I'm going to click on rectangle. And you can kind of see here it has a rectangle with 2 points. So that just means you can draw a rectangle by clicking where one corner is going to start and then going where one corner is going to end. Once you do that, you get this kind of shape here. After we have that general rectangle shape, we need to go ahead and dimension it. So in this menu here, one of the things besides draw and modify is dimensions. We'll go and click there, and we have horizontal, vertical, radius, diameter, a bunch of stuff. We could use general and click on a line segment, and this is what it's going to look like for you. Then you click anywhere, kind of like you're dimensioning something for a drawing in SolidWorks, and it will show up here. You can see that as H1 on the screen, so I'm going to go ahead and find that on the left-hand side, and it defaulted it to 23 meters just because it's an arbitrary shape that I made. So if you click on this box here, you could replace that with 2 meters there. And then you're going to do the same thing for the height. And the height is going to be 0.25. And it made this appear on you because now it's really small in terms of like the scale of the drawing. To zoom in, at the top in the toolbar you have this magnifying glass with a plus. You can click that and then you could select which region you want to highlight. And it will bring up a rectangle with the dimensions that you specified. So now that we're there, we click back on the modeling tab, and now in the XY plane tree, there's a little plus sign on the side, and when you expand that, you have the sketch that we made, and when you select it, it'll go ahead and it will highlight the sketch in yellow. And everything here is for the CAD modeler I have with my version of Ansys, so it might look different for you, but in the end, all we want is a sketch of a rectangle. So the last thing we want to do in geometry is turn that sketch into a face. And up top, under concepts, there's an option that says surface from sketches. Go ahead and click on that. It's going to bring up another item here in the tree. And the tree here, and pretty much in any kind of Ansys window, it's either going to have like a question mark or a thunderbolt or a check mark. So thunderbolt means you've inserted something and it's waiting for you to put in more inputs. Green means it's good to go. So like our sketch here has a green check mark because we defined it and it's constrained, it's good to go. The surface from a sketch has a thunderbolt because we need to define something. So when you click on it, you have this menu here at the bottom. And as you would imagine, to make a surface from a sketch, we have to define a sketch. And by default, it selects the sketch that I had here. So it's selecting it because it's popping up in yellow. So once it shows up in yellow, I can hit apply. And it selected the sketch. Now it turns into like a light blue color. And the last thing that I do is hit generate. So up top in the menu here, you're going to have a thunderbolt with generate. You click that. And now my sketch goes from just a hollow, just from a bunch of lines to something with a gray area. So gray means this is a surface now and not just a sketch. And if you want to, there's these arrows here at the top for rotating it, and you can kind of just look at it and make sure like, yeah, this is in fact a face or a sketch or a face or a surface. Those terms are used interchangeably here. And like I said, this is a 2D analysis, so there's nothing wrong with the fact that our geometry is two-dimensional. That's the whole point of what we're trying to do right now. So once we have that, you're going to notice another item here in the tree. It's going to say one part, one body, and surface body. At the bottom here, it will give you some information about what you drew. So we have that it has one face, it has 4 edges, we have a surface area of 1/2 meter, which we should expect from 2 meters times 1/4 of a meter. So from this point, we could, yeah, so.
Hold it for a second.
Sure.
So how did you go back and make that a surface profile again?
How did I go and turn that sketch into a surface? So once you have the sketch, up at the top where you have concepts, if you click on that and you find this option called surface from sketches.
If you're using 18, it automatically will create the surface if it's a closed loop.
Okay, yeah, so this is a much
You
different
just have to
layout.
get out of the sketch, which I just did.
That's the easy, looks good.
I just selected like push pull or something, and then it took me out. But
Yeah, that looks a lot different.
yeah.
Yeah,
So
okay,
Yeah.
and it automatically created the surface when I got out of the sketch.
okay.
So where'd you find push pull?
I think it's under
About in the middle of that top.
design. It's under the design tab, and then I like just selected pull, I think, and then it took me out, and then it said, "Oh, there's a surface."
Yeah, so they're all on Ansys 18, so that's good, because I don't know where that is, but if one of you knows where it is, all of you know where it is, so that's good. So did you figure it out how to get a
Yeah.
sketch? Okay, cool. Excellent. So for this older version, if I just click out of this now, it'll bring me back to my original screen, and now I'll have a green check mark. I don't know for you guys, you probably just click out of the same thing too, it brings you back to the screen. So now we have green check mark by geometry, we could go on to model. So this is where the fun starts. Before we do that, I want to bring up, if you guys have seen or understood or seen in a class plane strain versus plane stress. Does that sound familiar? Do you guys recall more or less what it is or what it means?
Well, plane stress, is that like a projection of the stress tensor where it's like only in one dimension?
Not exactly,
Or
no.
two- yeah.
No. So plane stress versus plane strain, it kind of tells you what about the size of your body and what's going on with it. So if you imagine, should I draw this on the board or should I just use this picture here? Open image new tab. So we're doing a 2D analysis, right? So you can picture that as this figure here on the right. If we were just going to do a cross section of that right in the middle, right? That could be one option for what we're going to do in terms of 2D, and we'll call that plane strain. And the other one is if we have this block here and we're doing the same thing, we're doing a cross section of it, right? But the one on the left is really thin. So it's essentially like we're not even taking a cross section, we're just going to do the actual plate as it is because it's really thin anyway. Whereas on the right, the plane strain, it's a really thick body. So we're doing a cross section of this really thick body versus something really thin. That's all you really need to know for now. But I'll show you how it comes into play later. Yeah.
So plane strain is an approximation by adding a bunch of thin bodies to model a thick body, but a plane stress is an approximation, is a really thin, we're modeling an actually really thin body?
Yeah, that's one way you could think about it. You see here on the side, it says that in plane stress, all the stresses in the z direction are 0, but the strain in the z direction is not 0. So think about if you have this shape here on the left, right, and you pull on it in both directions in the x-axis. From Poisson's effect, it's going to shrink in the z-axis, right? So that's where the strain in the z is not equal to 0. It's not equal to 0 because it's free to shrink, right? Whereas the figure here on the right, if you pulled it in the x direction, right in the middle of the body, the strain there is 0 because the body cannot shrink because there's more material on both sides of it. So in the left side here, it's free to constrict in the z direction because it's really thin. Whereas on the right side, it's so thick that all the material on both sides of it is preventing it from straining inwards. Also, in terms of that, because this one on the left is free to move where it's free to constrict in the Z direction due to a force in the X direction. There's no stress in the Z direction on that free face. Whereas if you looked at the cross section right in the middle of this thicker one here, when you're pulling in the X direction, there will be a stress in the Z direction. Kind of complicated, but it will make sense as we're doing the analysis. Hopefully, I think it will. So let's go back to Workbench and go ahead and double click on Model. That's just like something that you need to know in terms of like when we start to click stuff and put loads on the body in Ansys, you'll get a result, but then you have to see, okay, is what I'm modeling physically representative of a real body? And we'll go back on that once we get some results here. As soon as this opens up for me, come on. Okay, so when you double click on it, it'll say in the corner, starting mechanical. That's one way to know that it's opening after you double click on it. And does this look the same for you guys on 18, or does it look a bit different?
Still loading.
Still loading?
It's
Okay.
still loading.
Yeah, it's a lot of information. While it loads, I'll talk through what we have here. So you have this generic tree. You have a model, geometry, coordinate system, mesh, static structural, and solution. So if we click on model, a lot of the options I'm going to talk about are going to be in the bottom left-hand corner here. Model doesn't give you a lot of information. To be honest, it gives you pretty much nothing. If you double-click on geometry, you get a lot more information there. The most important one is going to be the 2D behavior. So now we have an option here of choosing whether we want to do plane stress, axisymmetric, plane strain. Those first three are the important ones. The bottom two, by body and generalized plane strain, those ones I have not used. But plane stress and plane strain are the two that we're going to use. Axisymmetric, that would be like if you're modeling a cylinder that's axisymmetric, you can just model a single slice of it, and it treats it as if you were revolving the whole thing around the y-axis, so you get that full 3D data by only using a single slice of your symmetry. So you could get the same kind of results and analysis from something that's going to run a lot quicker. Is it still loading up for you guys, or do you have it open?
Loading in. Can't seem to find that 2D behavior.
Under geometry.
Yeah, I'm in there.
Let's take a look. Geometry. You probably didn't click on. Did you make sure your geometry was 2D before you made it? So click on geometry. Yeah, so yours was 3D. So
Okay, so I gotta go back and.
you could try close out of the modeler and click on geometry, select it to be 2D, and then reopen a modeler.
Okay.
Yeah, but if that doesn't do it, then you have to go back, delete your whole thing, or you could right-click on geometry, and there's an option to clear it. And then you can double-click on it again, redefine your sketch. Are you guys able to open a model? Cool. Are you getting that? Or?
I think I've got the same problem here.
Oh, come on. Scrubs. I warned you. While you're doing that, I'll speak a bit more briefly on what we're going to do here. So where was that? So I'm going to go and select plane stress for now, because plane stress is the simpler one. Plane stress is, if you've ever seen a tensile test. So when they're doing this kind of test, right, the sample's very thin. So most commonly you do see a material in a state of plane stress. you rarely see a tensile test, if ever, in a state of plane strain, unless you have a really thick sample, and that's because you're really interested in like the advanced mechanics of how this material behaves with the extra constriction, that kind of stuff. So geometry, coordinate system, we're not going to do anything here. This is useful if you want to make pretty plots of stresses at different points, not what we need to do here. Mesh, if you click on mesh and if you right click on it and hit generate mesh, it will make a default mesh for you, and you'll laugh about how coarse this is, but I mean, we're going to use this mesh for a few loading cases, and it's going to show you that, like, yeah, this works fine. And it'll be a testament to just because you dump more nodes and elements at a problem doesn't mean you get any closer to representing physical reality. So once you're on this state, leave mesh just as the default one. Later, we'll go through and make it finer to study what's going on at the boundary conditions. Cool. So, like I drew on the board, we have this little beam, right? We're going to fix it on one side to a wall, and of course there's no like erasers here. Oh, cool, thank you. Yeah, I don't want to use my hand. I hate when profs do that. I erased that, but first thing we're going to do is we're going to put an axial load. We're going to do it at 10,000 newtons. Kind of arbitrary, but you know, we'll just go with it. So the two things that you need to do in this module here of static structural, you need to define the boundary conditions. So how this thing is hooked up to some kind of constraint, right? Because right now it's just like floating in 3D space. And if you put like a load on the right side of this thing right now and hit solve, you get a bunch of errors saying that this thing is like floating in 3D space and you're pushing on it and it keeps floating, it's not deforming. So let's start with the constraints. And once you guys redefine your geometry, I'll make sure that you're at this point too. If you right click on static structural and hover over insert, you have a bunch of different options. The ones we're going to focus on are going to be force here, fixed support, and displacement. So the first one I want you to click on is fixed support, and you're going to be able to, at the top here, you have the option to define it for a point, an edge, or a face. So that's crucial in terms of like what you're trying to fix. And this is going to be another thing you learned probably in the deformable bodies class. So the way we're going to what's the word? Constrain this thing is you're going to have rigid, like a fixed point at the bottom, but at the top we're going to do a roller constraint. So this is going to mean that this point can move in X or Y. This point cannot move in the X direction, but it's free to move up and down in the Y direction. This is Y, and this is X. And the reason that we need to do a fixed support here and a roller there is because as we push on this thing in this direction here, it's going to want to expand in that direction there. So by not letting this expand up and down in the Y, we're creating an additional constraint that we don't want to impose at this point. Yeah.
Ansys can solve indeterminate structures, right?
Yeah, yeah, it could do that. Yeah, it just like when you look at the plots of what's going on, they're going to look different, and it's good that it can do that because then when you're at the point where you really know what you're like modeling and how to constrain things, you can use that to your advantage. But the only reason I'm doing it this way is to get people, you know, if you never used it, how to go about doing it. So we clicked on fixed support. We're going to click on this point here, right? And you know you're doing it right because once you click on this, you'll only be able to select a point, right? You can't select the face or the edge. So we're going to go ahead and constrain the lower left-hand point. Once you click on a point, it's going to turn green. You hit apply, and the fixed support here now has a green check mark, meaning that you're good to go.
Where's the apply button?
It should be in the lower left-hand side here. So let me do that again for you. If I have fixed support, do you see it here now?
Yes, I see it now.
Okay, yeah, cool. So let me get rid of this thing. The next thing that I want to do is instead of fixed support, I'm going to select displacement. And the two options for displacement of a face, an edge, or a point is it could be free to move as it needs to, or it could be 0, meaning that it's fixed. So we're going to do displacement. We're going to select the edge command here, and we're going to go ahead and we're going to select this whole left edge, and we're going to hit apply. You're going to see 2 yellow boxes in the corner. By default, they both say free. So right now, by clicking on the edge and leaving it as free, we don't really do anything. But what we're going to do is we're going to set the X component to 0. So what this is saying is that face is free to move up and down in the Y as it needs to, but it cannot move in the X. So it's like a roller constraint, but for the whole surface, essentially. And that's what we want to do at this point. So we have a fixed support on the bottom. The fixed support binds it in X and the Y, so now we like fixed it in 3D space, but you could picture like it could just pivot around that one hinge, right? So the displacement now fixes it so it's not rotating like crazy. So these 2 constraints are all we need to properly fix this beam that we have. The next thing we want to do is insert a force. We're going to make sure that we apply it to an edge. We're going to click the right edge, make sure it's green, hit apply, and the yellow box we have right now is magnitude, and right above that it says defined by vector. So you could change vector to components, and you could select it instead of one absolute vector of force, you could split it up into how much force do you want in the X, how much force do you want in the Y. So we're going to put negative 10,000 newtons in the X to push on this thing and compress it, and 0 on the Y. Does anyone have any issues about putting the loads or supports? Yeah, what's up?
Oh, I got it.
I guess.
I was trying to put the unit in.
Okay, yeah. Ansys is nice is that up top, if you click on units, it has a bunch of defaults for you. Yeah.
Is there a way that I could fix my graphics tab? Because every time I move to the outline, my graphics start to disappear. So like if I'm trying to select a fixed support, then
Yeah. Oh, that?
Yeah. you can just kind of play with it and see.
Yeah.
They don't need to do it.
Hopefully, I mean, that can be annoying too. One of the worst things about Ansys or FEA is that 90% of the time you just don't know where that button is, or you know what you want to do, but you don't know where the option to select it is, and that's a pain. What I was saying is with Ansys, it has all these predefined units at the top, whereas Abacus, which is another really, really popular program for FEA, it doesn't keep track of any units, so you have to do it on your own, which is good in the sense that if you know from the start, like you're using units of pascals, millimeters, newtons, or whatever, you're good to go, but you know, whatever. So we have supports and we have a force. So now we have enough information to solve, but we need to tell Ansys what we want to solve for. So under solution, if you right click there and hover over insert, we have stress tools, we have deformation, strain, stress, a bunch of stuff. The one we want to select for now is we'll do normal stress. And go ahead and insert normal stress twice, because when you insert it, in the lower left-hand corner, you have orientation, and by default, it's in the x-axis. So one of them, we're going to go ahead and change to the y-axis. so we can see what the normal stress is in both directions. Also, go ahead and insert the stress for equivalent or von Mises. That will be an important one as well. A small thing, since we have two normal stresses, if you select them both, if you right-click and click on rename based on definition, it'll just rename it for you so you know which one is which. You could also, when you're selecting it, hit F2 and name it whatever you desire to not take up as much space. So insert the normal stress in the X and the Y and the equivalent stress. Also insert the deformation, both total and directional. Total, you don't really change a lot. In the directional, it's in the x-axis by default, so we'll leave it there. What's up?
Yeah, mechanical crashed,
Oh, like it's not responding, or?
as in it exited out and then said unable to view geometry, unable to get model.
Oh, everyone's saved right now. I'm gonna do the same thing. Because that happens, yeah. So I'm just gonna say, let's go to MISC, project 1. See if you can recover it, but if not, you might have to go through all the stuff again, of course, with saving stuff this time. But that's a common mistake when you first get started in this kind of stuff. So we have our supports, our force, and a bunch of thunderbolts on the stuff that we defined that we wanted to solve for. So now I can right-click on solution and hit solve, or hit solve on the top here. We'll do the same thing, and we'll go ahead and we'll solve the problem that we posed. You might get some issues here, some error messages. 9 out of 10 times, Ansys might tell you that you're doing something wrong, and you just have to know that it's doing exactly what you typed in for it to do. Kind of like MATLAB or programming. If there's an error or something doesn't work, it's because of something that you did. Were you guys able to get back on there, Tori, or after your thing crashed?
Mine?
Yeah, because you said you had to redo your geometry.
Yeah, mine's not communicating with geometry, so I've just been watching.
Ah, okay, no worries.
A little far down.
It seems like, yeah, Ansys is not extremely user-friendly.
Some error messages till a bit later.
Under solution information, if you really want to know what's going on with every load step that it's doing, it writes everything to a text file. But, unless you're doing something really complicated, you wouldn't really care about that kind of stuff. But let's start looking at what stresses and strains we get, right? So we'll start with the stress in the x-axis. Stress, as everyone knows, is force over area. So we have a force of 10,000 newtons, and the question now becomes like, what's the area, right? We're doing a 2D shape, so we don't have any kind of thickness. But the way ANSYS calculates this, it just gives you a unit thickness. So it assumes that the thickness is 1 meter in the depth of the board. So let's see what we're supposed to get for stress, right? So our force is 10,000, and our area is the thickness that we made, or the height of the beam, 1/4 of a meter times 1 meter. So if we do Fx over A, we're supposed to get 40,000, right? Which is what ANSYS gives us here. And you'll note that it's negative 40,000 because it's in compression. If we pulled on it, we would get a positive number here. You also note that our mesh is very, very coarse, yet it can tell us, that the stress is what we expect almost everywhere. Or, I mean, not almost everywhere, but exactly everywhere. So we know that it's doing its job right. In terms of y-axis, it's not a uniform color, right? And you have a color scale here. But if you look closely at this, pretty much all those numbers are e to the -9th. This tool over here, probe, lets you hover over a point, and it will tell you what the stress is at that point. And even though the stress is not uniform at every element, it's pretty much 0, which is what you expect, right? You expect no kind of stress in the y-axis. the equivalent stress. So this one is also 40,000. This is going to be different when we do plane strain, because what we've been doing is plane stress. Total deformation. So now we get something a bit more interesting. We have total and we have directional. So let's look at the directional first. The directional strain is 0 where it's red and -4 times 10 to the -7th where it's blue, right? So if you look at this plot, intuitively it makes sense in the sense that if you're pushing on this side, all the deflection is here and it's in the negative x direction. So as you get closer to the beam, the deflection here is pretty much nothing, right? So that's another like sanity check to make sure that what we're having Ansys solve is reflective of a reality. Does anyone know what the equation is for the deflection of a beam?
Is it normal force divided by Young's modulus times length over area?
Yeah, that sounds right. Yeah, PL over AE is how I remember it. So E was 71.7 times 10 to the 9th. So displacement is equal to our force of 10,000, don't need the comma, times our length of 2 meters divided by our area times our Young's modulus. Did I do that right? P L over AE. So I'm getting something that is not 4 times 10 to the -7th. And I did this yesterday, and I ran into the same issue. So let's see what I did wrong. Anyone have any guesses? PL over AE.
So you calculated the stress properly, but not the deformation, right?
Correct, yeah. And this is, yeah, so see, this is one of the things where you want to do like an FEA analysis of a complicated thing, right? But you start with a beam, and you just push on the beam, and it's deforming not what you expect it to deform, you know, red flag, like something's not doing what it's supposed to be doing. So let me see what I did yesterday to fix this. I divided by 4. Why did I do that? Let's make sure I define my stuff right. So engineering data, aluminum, 71.7, so it's the same as 7.17 times e to the 10th. So that's right. Geometry, thickness of 1 meter by default. Okay, that's what we expect. Length of 2 meters, height of 1/4 of a meter. So our area is supposed to be, yeah, 1/4 of a meter. Oh, no, that's right, yeah, our force is 10,000. What did I do wrong? Anyone have any guesses?
Check your boundary conditions.
Yeah, that's a good one. Fix supports. Free to move in the Y, constrain in the X. Fixed at the bottom there. 4 to 10,000. This is where I go to my handy dandy. This is a book that I sent previously in the in Slack. That's not it. This is a book that I used for a senior level course at Rose-Hulman. It has a couple of chapters on stress and strain, one on materials, one on fatigue, one on like if you're building something, what size of nuts and bolts to use, that kind of stuff. It has one chapter on deflections. Let's see. Oh, did you find the where I sent it?
Yeah, it's an analysis now.
Okay, yeah. Directional deformation. Am I looking at the wrong thing? No, strain. I don't know, guys. I don't know what I'm doing wrong. Death by demo. Oh, well, we're going to move on anyway.
Did we show anything useful from the book?
This is generally a useful table of like deflections and deformations, that kind of stuff.
I just, there's more general thing if I'm putting.
Oh, yeah. No worries, yeah. Yeah, I definitely recommend you guys like just all look through this book. Not like study it, but then in the back of your head you have, oh yeah, there's this one table in the book that can help you on this or that. Okay. Cool. Back in Ansys. You know what? I'm thinking it's the mesh density, because that's something we didn't touch on. It's fine for the stress, but let's beef that up. So I'll make this free to move in the Y, so I'm going to change everything back. I just tried a bunch of stuff to see if I could fix that, but that might be what's causing the issue. Go back to compression. So mesh, when you right click on mesh, you have a lot of different options to refine it. You could define it in a certain area of your body. You could define it close to a line or to a point. We're gonna do a really basic one. If you click on sizing, you have this yellow part over here. So here you input the geometry. So it wants you to select where you want to refine the mesh. So you'll see it's not letting me click right now. I need to go ahead and click up top here on the face. It turns green, then I can hit apply. This comes in handy if, say, I really wanted to know what's going on at the wall here. I could split this face up into different sections. So it'll be the same surface, but with 4 faces, and I could select just a face closest to the wall, refine the mesh there to have more elements there, keep it coarse far away where I don't really care about what's going on. So I select the face, and then over here under element size, you could select it by that or sphere of influence. I'm not sure what that one does or if I've ever needed to use it, but we'll stick with element size. And we're going to input 0.1, and we're going to see what that looks like. This is a part of the, okay, so that's what it was by default. So go ahead and click on that again, and we'll make it, instead of 0.1, 0.025. Let's go 0.5. Sometimes if you if you're kind of bold, you'll make that number really small, and Abacus will try, or Ansys will try to make a mesh for like 5 minutes or 6 minutes, and you're not sure like whether or not it's going to crash or not, or whether it's going to go ahead and make the mesh that you want to do. So this is still kind of coarse, so I'll change that to 0.25, so half of what I just had right now. So then we get, okay, yeah, so this is a lot more elements. So I'll go ahead and I'll hit solve, and we'll see if that fixes the issue I had previously, and if not, we're going to try and move on anyway. So stress in the X is the same as before at negative 40,000. Stress in the Y, so now you'll notice that more of the entire surface is the same color. There's only a little bit of discrepancy in the corner here. So the orange, let me zoom back out on that. The orange, if you probe around, it's E times 10 to the negative 8 or 9. So everywhere in the beam, the stress in the Y is 0, except when you zoom in at the corner here. And to zoom in, there's the magnifying glass with the plus sign. You could go ahead and define where you want to zoom in. If I probe around what's going on there, I'll get values that are only e to the negative 6 or e to the negative 5. Still pretty close to 0. But what this is showing you is that Abacus makes an artificial stress concentration. You know that in the entire beam, the stresses are supposed to be 0, but they're coming on, they're showing us something a bit higher in that corner. And you'll notice that this only happens in the corner where we have the fixed support in both the X and the Y. In the top of the beam here, it's fine here, right? Here we're not being as constrictive. We're letting it move in the Y as it needs to, but not in the X. So this is a testament of when you apply a boundary constraint, it's going to create an additional stress. And you have to know whether or not that's a physical thing or if that's just the part of the math that it's solving for you. So let's zoom out again. Total deformation, directional deformation. So this did not change. So that didn't change my issue there. Oops. I just rotated it by accident. If you ever like rotate into a weird spot, oh yeah, and it like makes it into a 3D shape to make that like thickness of 1 meter. So that's what it's doing here. That's why it like looks pretty funky. But if you click on just Z, it brings you back in this face. Yeah.
How can you find maximum in-plane stress, stuff like that?
Maximum in-plane stress. If you click on this guy here, max, this will automatically make a little thing that says, okay, here's your point of max of whatever you're looking at. It does the same thing for min. So min would be on this side here. But you're asking if where you have the maximum stress, like that,
like
that you really.
maximum in-plane shear stress, like on a stress on a component. Yeah.
Okay, yeah. So that would be the one thing you would want to look at is the equivalent stress. So that would be like your combination of all your normal stresses and your shear stresses. It's showing up as the same thing throughout the whole beam here, just because we're doing something really simple. So let's move on to, instead of putting a force that's putting the beam in compression, let's change this to now push it straight down. So we're going to get rid of the force in the X, put that to 0, and we're going to put negative force in the Y of negative 1,000 newtons. So now your arrow is going to point down, and that's an easy way to know that you're doing it right. We'll leave the constraints at the left side of the beam the same way, fixed at the bottom, and making sure that the left edge cannot move in the X direction. And after you make that change, let's hit solve and investigate what happens now. Instead of compressing it, we're going to see what happens to the beam as it bends. So now we have something a little more interesting. Let's first look at the stress in the y-axis. So it's red on top, it's blue on the bottom. From your deformable bodies class, you know that when you bend a beam, like in the picture here, the top part is being pulled apart, so this part is in tension. The bottom part is being compressed, so it's in compression. That's why these values are positive, these values are negative here. It's most intense at the point where you constrain it, and it eventually goes to 0 the closer we get to the edge, right? So it's dying off, and you know, it's 84 right at the edge, pretty much 0. These numbers aren't exactly 0 because you have to recall that this method of finite element, it's an approximation. It's not exactly what's going on. You know in your head that it's 0 at the edge of the beam, but just because it's not giving you 0, that doesn't mean something's going on wrong there. And more than likely, you don't care that this value here is 69 or 892. You care more that the maximum value here is 171 or 1.71 times 10 to the 5th. If we click on y-axis, we get something similar to what we saw before. Everything is 0-ish, 3, 1 times 10 to the negative 3, everything's 0. Except we're getting the same kind of weird behavior going on here, right? But now it's not really close to 0. Now these values are a lot higher. So this is another point of if you're bending this beam and you wanted it to tell you where's the max stress in the y-axis, this will tell you it's right there, and it's going to tell you it's about 100,000. But you know that that's not true because in reality there would be no stress in the y of that magnitude. And we're going to run this case one more time by tweaking the boundary constraints a little bit. I want to go back on this point of the x-axis, or the stresses in the x-axis. Everything in this beam that I've done is symmetric, so the normal stress at the top of the beam should be the same magnitude as the bottom of the beam, except flipped in directions. If we probe these values, not exactly at the corner here, because we know at the corner they're not realistic. They're more realistic a few elements away from a boundary constraint. Really quick, let me make another attempt at verifying what I'm trying to do. So do you guys know what the stress is from a bending moment? I think it's my over I. Does that sound familiar?
Yeah.
Yeah, that's what it is. So bending stress, that's equal to the moment that we apply. So the moment is the force times the moment arm, which is the length of 2 meters times the force of 1,000 meters, or of 1,000 newtons. Y is the distance away from the neutral axis. So if our beam is 0.25 in height, the max we could look at is half that, 0.125, which is right at the surface of the top or the bottom of the beam. 25, and we divide by the second moment of area, which is your base. Man, it's complicated, but that's the because we're doing a 2D example. Ansys just assumes that your thickness is 1 for everything that you do, times your height, which is the height of the beam, 0.25 to the third, divided by 12. So this gives you 1.92 times 10 to the 5th. So if we look at the values here, 1.71 times 10 to the 5th. So we're in the ballpark. This would be a big issue if we're like off by orders of magnitude. And the maximum stress should occur right here, right? So we're at 1.88, 1.89. So that's really, really close to 1.92. If you want to get really particular about it, you could look at your error that you're off by. So we're going to do what we know we're supposed to get analytically minus what we got in the program divided by what we're supposed to get. And that gives you an error of 2%. So an error below 5% is considered pretty good in FEM. So we know we're on the right track there. So that's at the top of the beam in tension. Oops. Let's look at the bottom of the beam. What's going on there? So here we have 1.32, 1.78, 2.175. So here we're getting values that are much, much higher what we expect. So this kind of shows you that the stricter the constraint is on geometry, the more it's going to skew what answers you get compared to what you're supposed to get. The other thing we need to look at is the equivalent stress. So this plot looks a bit different. This plot is the same color on both the top and the bottom, and it's only positive. Its minimum value is 3,000. Do you guys know why that is? Why it's not negative?
Isn't equivalent stress like always the maximum and it's like the absolute value?
Kind of. It's not the absolute value, but you're looking at the combination of all the stresses. So this equation here, this is what you use to calculate the von Mises stress. I touched on this a couple of times at a meeting, but the von Mises stress is important because if you're looking at this kind of beam here, right, you have this stress in the x-axis, which is very high here. Not considering at the bottom here where it's not realistic, but at the top where we know we're supposed to get 1.92 times 10 to the 5th, we get really close to that, right? So say we had a case where the stress in the x is very high, close to our yielding point, but the stress in the y is 0. You know, what does that mean about if the material is actually going to yield or not? So the von Mises criterion is a way to take all your stresses at a point in all three normal directions and all three shear stresses and combine them into this one value of stress. And this value of stress is what you would compare to, is what you would use to compare to the yield strength to know if your material is actually going to yield or not. I have this one plot from my plasticity class that's interesting.
By the way, is the von Mises an overestimate of your maximum equivalent stress, or is it more or less dead on?
Maximum equivalent stress. It could be lower than your maximum equivalent stress because your equivalent stress, there's a couple of different ways you could define it, to be honest. Let me see if I could find that plot though. Here. So what you're looking at in this plot is if you plot the stress in the x direction as here, and the stress in the y, right? And this this oval-looking thing is the von Mises stress criterion. So this is like mathematically the shape from this equation here, if you just consider it in the x and the y two-dimensionally, right? And all these points here are experimental data points from metals. And the reason we use von Mises primarily is because mathematically it has some kind of basis and it fits well with experiments. There's a lot of materials that don't fit it 100%, but it's really close. So that's why we use it. Another kind of cool thing about this plot is in this corner here, we have positive x and positive y, right? So that's like if we had a cube and we're pulling on it in this direction and in that direction, the material is going to want to plastically deform when you need more stresses if you're applying that force in both directions for it to plastically yield, as opposed to here, right, where we have positive x and then a negative y. So you're pulling it in this direction and you're squeezing it in this direction. That's gonna make it easier to deform if you kind of like think about it. Like if you're trying to deform, I'm trying to think of something like physical, like what's something elastic that you could like pull apart?
Rubber band.
Yeah, rubber band is a good example. But this just, at least gives you some kind of understanding of, why we use these kinds of things. Any kind of questions about that? I know I kind of went on a rant of a lot of stress stuff that may not make sense. Yeah.
Is the von Mises or equivalent stress like the eigenvector, eigenvalue of the stress tensor?
Yes, it is. Indeed, it is. And I think it shows it here. So there's something called a stress invariant. Okay, a lot of good stuff here. Let me see which picture that shows this best. Invariant. Okay, that's not going to work well. Okay, this picture helps. Where was it? You guys remember Moore's circle? Moore's circle was, you have a 2D stress element, and it has forces in the x and in the y, and it has shears too. And the point of Moore's circle was to realize that if you were to rotate it, you get it to a point where it has no shears, but it has higher stresses in the x and the y. And it kind of helps you realize that even though your stresses in the x and the y were only 10 newtons with the shear stress, now they're 15 if you rotate it in a certain point. So essentially what you're doing with the von Mises and the invariance is you're now doing that in 3 dimensions. You have nine stresses, and those stresses make a 3x3 matrix, and you could rotate it a certain way where you only have normal stresses and no shear stresses. And because you could put those 9 stresses into a 3x3 matrix, if you solve the eigenvalues for that 3x3 matrix, one of the things that you get out is the value of the von Mises stress. And that's kind of cool. It's called the invariant, because if you're in this state here where you have values in every point in this 3x3 matrix, and then you rotate it where you have no shears, only normal forces, which means that this matrix now only has values in diagonal, no shears. If you do the eigenvalue problem and find the invariance of both of those tensors, they give you the same thing, which is why it's called an invariant. It doesn't vary based on how you're looking at it, right? These two elements only differ based on your reference choice of your x, y, and z axis. Yeah, that's where it comes from. Yeah.
And failure theory, metals fail in shear, right?
Correct, yeah.
So why would we look at maximum plane normal stress when Coulomb-Moore says that they fail, that when we reach maximum shear stress, they fail?
Why are we looking at the stress in the x direction in Ansys?
Why is equivalent stress maximum normal stress and not maximum shear stress on a stress element?
Let me show you. It kind of comes down to. So this is some slides from my plasticity course. You recognize this as a stress strain curve in 1D, and essentially this plot here, all these points are where the material started to deform plastically, where the von Mises stress was high enough to overcome the force necessary to shear individual atoms on a plane. So you know, the reason we look at normal stresses is because those normal stresses, when you use them in the equivalent stress equation, they let you know how close you are to this yield point, if that answers your question. Okay, cool. Yeah, it's a lot. I definitely did not have much of an appreciation for this in undergrad, but it's a lot of stuff. It's pretty complicated. Any other questions? Thoughts? Cool. What else can we look at? So, okay, let's go back to bending. Because I wanted to. Do I want to go back to bending right now? Really quick, I changed back the force to be compressive on the right side. And when we looked at the stress in the y-axis, it was doing weird things only on the bottom here, not on top. So what I'm going to do is go back to how I constrain this thing. I'm going to suppress the fixed support. Where's that? Suppress. And under displacement, I'm going to change free to be 0 in the y. So now I'm able to fully constrain this piece in 3D in my 3D space with just displacements, and this left edge cannot move at all. And I'm going to hit solve. And the difference in what it's doing now is instead of being deformed in a rectangular shape, because this whole face is fixed, it's going to do something where it bows out like that due to that force. And that's going to create some weird stuff in the stress in the y direction here. It also made some weird stuff in the x direction, right? So previously we had that the stress was being calculated correctly at 40,000 in the entire bar. But now we have really weird stuff that's going on. It gets as high as low as 38,000 pascals, 37 there, and then it gets really high up to 60,000 there. These stresses here, they don't make sense because they're really close to the corners. This stress over here, even though you might think that those stresses are not correct, those are actually fine, because what it's doing is it's got this weird deformation going on here. So the stresses here are going to be a little bit different in order to make this endpoint work. So sometimes you have a stress concentration that you think is artificial because of what I showed you previously, but you have to look at how close it is to the boundary that you fixed initially. So this is the stress in the x. The stresses in the y are now not just weird at the bottom, they're weird all throughout the edge, and they kind of like bow out. If we look at everywhere else in the bar again, everything's 0, except on that edge. So let's see just how weird they are. Negative 10,000, yeah, that's pretty bad. It gets better the farther away we get, but the closer you are to the edge here, it gives you nonsensical results. If we look at the equivalent stress of just compressing it, it gives you the same value all throughout the 40,000 that we expect, except at the wall. And this usually presents an issue because if you're analyzing something like for the rocket, some type of, say it's the fin, right? If this is the fin on the rocket and you're analyzing all the distributed load that's going to act on the whole thing here, right? You don't really care what's going on right at the edge of the fin. You care what's going on here where it's attached to the fin. So that's where you have to be really careful in terms of how you make the FEM solve the problem you pose to it.
Could you just because of the way physics works, every action has an equal and opposite reaction, right?
Yeah.
So just fix it on the other side and apply your load at the interface with the rocket, right? Would that work?
I think I know what you mean, but one way to answer that is like there's a couple of different ways to get around the artificial stress concentrations created by the mathematics here. One of them would be like if we were trying to model the same thing here, but we're worried about our boundary conditions creating some issues for us, right? We could make a geometry where we do something like this, right? So now this is part of the rocket, and this is the fin here. And we have to fix this somewhere, so we're gonna fix this whole thing here. And now we do our same compressive thing here, or our bending load here. Now all the stresses we get here, they're gonna be fine because they're not mathematically restricted to not moving or some other kind of weird thing. But now you get to a point where sharp geometric discontinuities can also give you an artificial stress concentration. And we'll go ahead and we'll do that for the remainder of the course. I'll show that.
Give you real stress concentrations too, though.
Yeah. So yeah, I'll touch on that too. And yeah, it shouldn't take too long. So what I'm gonna do is I'm gonna make another static structural thing. What I'm gonna do is, okay, I didn't mean to click there. If I hold and drag engineering data, it copies it over from the first one to the second one, so I don't have to redefine it. And I'll do this kind of fast, but it's recorded and I'll be here so you guys can ask me any questions. So I'll go ahead and I'll make that 2D before I click on geometry. And I'm going to draw just something really basic. Gonna look at this face. Line. So I'm gonna draw this thing that I drew here, and I'm gonna make the top of it with a fillet, and the bottom is going to be a sharp corner. Length is going to be very arbitrary here because I'm just trying to show what's going on with the stress concentrations. That was ugly. How do I delete trim? Draw line. I'm going to use the tool trim to get rid of this ugly piece here, and then I'm going to put a fillet. I think I could just select these two things. Okay, and it gives me an automatic one there. And I can make it a little bit bigger if I want to. We'll make.
Is there a way to import geometry from, say, AutoCAD?
Yep, that and SolidWorks, any kind of CAD modeler that you might use. I recall that in SolidWorks, like you just have to save it as a certain like IGES file or something like that. Yeah, but you could definitely do it. Okay, so I have my very arbitrary sketch, and I'll go on surface from sketches, and I'll generate that surface. It gave me some kind of error. Maybe I need to define all my all the dimensions. So let's just make sure everything's defined. even though it's arbitrary. So now it's over constraint. Oh, come on. Okay, I gotta start over. And I know this is probably an inefficient way to draw what I'm trying to draw, but I haven't cut it in a long time. Modify, trim, fillet. There we go. The issue I was having was when I was selecting the sketch, it wasn't selecting every single line. So I think something that I drew before wasn't connected. But I have a nice arbitrary shape now. So now I'll go on modeling. I'm going to just fix one side. I'm going to pull on the other side, and we're going to study what's going on with the stress concentration. Cool, okay. Let's look at the default mesh. The previous one, the elements were all nice and square, which it usually does for, if everything's nice and square, but it knew something's not super great here, and it started to do this. I'm gonna leave that as it is, and we'll kind of see what happens. Ansys doesn't have, it doesn't know what you're trying to solve. It's gonna give you something to start with, but you just kind of have to know what is an adequate mesh. So I'm going to fix this whole side. Actually, I'll be a bit better about that. I'll constrain it in the X, but I'll do the same thing where I just have a point, and I'll let the surface constrict in the Y if it wants to. Fix support point there, and
Can you use the displacement to have pre-strain on your structure?
probably, yeah. You could probably also do something where instead of like defining a force, you could, it's probably here too. So I could define a displacement on this left side, and it'll be the same thing as like an imposed strain too. Yeah, but you could definitely do that. Then, oops. I want to do that in the X direction. I want to pull on this thing. Okay, so we have a mesh, a poor one. Everything's constrained. And I'm curious in the equivalent stress and the normal stress because I'm pulling on that direction, so I want to see what's going on in that direction. And we could look at other stuff later, but let's see what this gives us. And we're going to be interested. Oh yeah, see, it's pretty bad. I'm trying to think what, yeah, I think looking at the stress in the X will be fine in terms of trying to see what's going on there. Because the stress in the X is the one that's going to be amplified by the fillet. So we have that it's around 1,000 on top, around 1,200 on the bottom, but the mesh is kind of, so let's go ahead and just improve that now and see what we get. Insert sizing. So this time I'm not going to put 0.1 or 0.01. Does anyone know why?
Because it'll try to go really small around the circle.
Yes, but also because previously our beam was 2 meters long, where now this thing is 30 meters long. So if I put 0.01 into something that's 30 meters long, it's going to crash on me. I've had times when I was doing something in 3D and I like put an extra 0 and it tried to make the mesh and like then it stopped responding and then I had to pull my battery out because like it ate all the RAM and like that was that. So be careful there. So well, let's go 1. That'll be pretty adequate. Okay, yeah, that's a lot better. So let's solve that. So it should give us a much more realistic stress distribution now. And that does look a lot better. We'll look at the equivalent stress for this. So I know there's an equation for it too, but I forget what it is. But usually like if you have like a hole in a plate where the plate's infinitely big, if it's 3-dimensional, the stress right at the hole is going to be 3 times the far field stress that you apply. In this case, the more or less the far field stress is around 918. And close to this bottom hole here, we have a peak of 1,300. I think if you have a hole in a plate in a 2D sample, the maximum stress at the hole is only twice your far field stress. So I expect this to not be, anywhere from like 2 to 3 times as big as the far field stress. But at the top, you have a stress of 1,800, right? Which is higher. So you might think, okay, well, all that really means is I have to dump more elements there. So let's do that, and we'll see how that changes things. I have a decent amount of RAM in here, but how do I want to do this?
Is there a way to like only locally increase the?
There is, yeah. So we're going to do a refinement, and you could select where you want to do this. So I could select these 2 faces and this face here. And we'll stick with that for now. We'll see how that looks. And then you have an option of saying a refinement of 1, 2, or 3. We'll start with 1. And as you can imagine, if you put it at 3, it'll refine it more. So see, it like, made more elements there. If we really wanted to go to 3, that shouldn't make anything crash. Okay, yeah, so now I have a lot of elements there, right? So let's go ahead and solve that. What might throw you off is the transition from these coarse ones to these fine ones. Usually, that's fine. That's not a super big red flag. But it's just going to come from experience, whether or not the transition that you see here, whether or not that's really going to influence what your answer is going to be. Any questions or anything? Cool. Let's solve this. Look again at equivalent stress. I imagine this one's going to stay the same at the bottom. It's not going to change too much. Now the far field one, it's still about 918. 1433, so around the same as what we saw before. At the top, the maximum stress is lower a little bit farther away than before, but when we get really close again, you know, it goes up to 3,500. So this is a perfect example of how if your geometry is kind of off, even though it's reflective of reality of maybe how you're building something, mathematically, you could make the elements like nano-sized, but the stress at the top here, it's just going to keep getting bigger. Every time you make the mesh smaller, it's going to keep getting bigger. Whereas the bottom one here, the stress at the bottom is going to approach a finite value, and adding more elements there isn't going to give you a closer result. That's a big thing in analysis, is distinguishing whether or not it's a real stress concentration or an artificial. Because like you said, right, you wanted to know where's the max. So the max is in fact there, but you know, does that really mean anything really? In terms of like if you have a physical part on the rocket where you have a really sharp transition like that, ideally it would be a fillet. If you can't put a fillet though, I'm sure there's like a hand equation to figure out what that maximum stress is there. I don't know what it is, but I'm sure it exists out there.